Hi, how do we study the convergence of a generic series with terms having a variable sign? In this video, through some examples, we will explore a strategy to tackle this problem. There are two general facts to keep in mind. The first is the so-called necessary condition for convergence. This is a condition that must be satisfied for the series to converge, but which is not sufficient to ensure convergence. The fact is that it is easy to prove that if a series sum of an converges, then necessarily its general term an must go to 0 for n going to plus infinity. In other words, if an does not go to 0, the series of an cannot be convergent. So it will be either divergent or indeterminate. This condition is often a source of confusion. Many students think that if an goes to 0, then the series is convergent, which is exactly the opposite implication that you see here. Of course, this is entirely false. A simple example of this is the harmonic series sum of 1 over n, which is divergent, and where you can see easily that the general term goes to 0. So this example should help you to keep in mind that the condition that n goes to 0 is not sufficient to ensure convergence. The second important fact is a sufficient condition. If satisfied, this guarantees the convergence of the series. Specifically, if the series of the absolute values of the an converges, in which case we said that the series of an is absolutely convergent, then also the series of an is convergent. The converse of this implication is false. So this condition is sufficient but not necessary. For example, if you take the logarithmic series sum of -1 to n times 1 over n, as we know this is convergent because of the Leibniz test, but it is not absolutely convergent because when we take the series of the absolute values, we have the harmonic series sum of 1 over n, which is divergent. Now, how can we combine these two conditions to study the convergence of a series with the general sign terms? We can imagine a two-step strategy. In the first step, we test the absolute convergence for the series. If this is verified, then we know that also the series of an is convergent. The nice thing is that this is a positive term series, so we can apply all tests known for this type of series, like comparison, asymptotic comparison, root and ratio tests. If the absolute convergence test fails, we could check, and this is step 2, if the necessary condition is verified. The good case is when this is false, because in this case, we could conclude that the series is not convergent. But if the necessary condition is satisfied, well, then all that's left is to light a candle for St. Anthony, as we say here in Padova. Now, let's see this strategy in action with a simple example. Here we have the series sum of x to the n over n, where x is a real parameter. Let's begin with the absolute convergence for this series, so the convergence for the series modulus of x to n divided by n. Now, since the modulus of the ratio is the ratio of the modulus, n is positive, and the modulus of x to n is modulus of x to the exponent n, we get this series that we can call series of Bn. Now, to this series, we can apply one of the known tests. For example, let's check with the root test. So we compute Bn to power 1 over n. This is modulus of x to the n divided by n to 1 over n. Now, by using properties of powers, in particular power of a power, we get modulus of x divided n to 1 over n. And since this last goes to 1, as we have seen many times, this limit is modulus of x. We call this number q. Now, according to the root test, we have that if q is less than 1, then the series of Bn, which is the series to which we are applying the root test is convergent. So this means that the series of modulus an is convergent. And therefore, because of the sufficient condition, this implies that also the series of an is convergent. If q is greater than 1, then we know that the test says that the series of Bn, which is the series of the modulus of an, is now divergent. This is not sufficient information because, as we have seen with the example of the logarithmic series, we may have that the series is convergent but not absolutely convergent. However, do you remind anything else that the root test says in the case q greater than 1? Yes, that's right. It says also that Bn goes to plus infinity. Bn is the modulus of an, so this goes to plus infinity, and in particular, it cannot go to 0. So an cannot go to 0. So the necessary condition is not verified, so we have not convergence. So, doing a recap here, for q less than 1, so this means modulus of x less than 1, we have convergence. For modulus of x greater than 1, we have not convergence. And what about modulus of x equal 1? Now, this is the case when q is 1 and the root test failed, so we cannot expect anything else from the root test. But since this means that x is just two possible values, plus and minus 1, let's see what happens directly on the series. For x equal 1, the series becomes, you plug 1 here, you get 1 to the end over n, so 1 over n, which is a divergent harmonic series, so we can conclude that our initial series cannot be convergent. If x is minus 1, we get the series minus 1 to n over n, which is convergent. It is the logarithmic series. So the conclusion is that our initial series will be convergent for x between minus 1 and 1, with the minus 1 included and the plus 1 excluded. So as you can see, we have been able to discuss convergence for every possible value of the variable x. Well, I hope this video was helpful. What can you do now? First, of course, practice applying the algorithm we illustrated here. For instance, on the series you see here on the screen, a little bit more complicated, but with the same scheme for the solution. Then you should try working at a more abstract level, for example, by combining known facts to derive new results, such as proving this property. Good luck, and may the wind always be at your back.